fracture characterization. So it's a very wide subject, but it is overall the things which we implemented over the years, or Open Detect. We will focus a lot on Open Detect plugins of faults and fractures, plus Azimuth-Alevio and those things. So just to give you up for the next few talks as well, like there would be neural networks at it was applied before it became deep learning. So, so it was, we could call it shallow learning sometime. So we'll go over all the previous applications from 90s, late 90s till now, what have been applied till the deep learning came in. So deep learning I will cover later, but that is include chimney and facies and those things. And then on 8th of April, like 2 Thursdays, we'll compare all the inversions, so at least the one which I know or I've used. So we'll try to compare them, the results on the try to same data set. And then this is the QStrat, is our quantitative stratigraphy software, which we kind of workflow which we are developing in order to clean up the LAS files and end up with the stratigraphic from the well logs. Then deep learning plugin and rock physics and pre-stack scenario modeling, and these for the inversion usually. That is the topics we have been, and then so give me enough time to announce the next topic. So hopefully, as long as we can continue, and we can invite Steve and those like to use the same slot, and then we can work that way. So I'm going to just introduce services of ours, fault and the fault and fracture analysis tools, conventional fault analysis, and unconventional fracture characterization. So in conventional, how it is applied on the conventional tools, and then Azimuth-Alevio, a brief introduction, Azimuth-Alevio, and then we'll conclude that based on this. So what services we do, we specialize in quantitative side and the attribute side, or interpretation services, and quantitative services. So quantitative include AVO, LMR, Azimuth-Alevio, various inversion types in the pre-stack domain, as well as in the post-stack domain with bunch of attributes, work, dip steering, deterministic inversion, various colored inversion, and we're coming into neural networks, as well as from the geology side, like a lot of cross sections, petrophysics, geology, well log analysis, and the quantitative sequence stratigraphy coming into horizon cube, Wheeler diagrams from the seismic. So it's really, we have done over the years, go through any workflow or just a part of the workflow. That's what we provide as a service, so that we can complement the exploration and development of the operators. So we worked over the years with, of course, based in Western Canada Sedimentary Basin, with all many areas here, then Houston, Louisiana, more say Louisiana than offshore, onshore, as well as Mexico, going to Colombia, quite a bit of work in Colombia and Argentina. Then on this side, which of course my origin, Pakistan, and work quite a bit with India. More recently, in last 5 years, we worked many studies in India, onshore, offshore, and then Kenya, Tanzania, rift basins, rift systems with chimney analysis, and various work in Chad and Nigeria. And recently with North Sea, some of the well data work in the North Sea. So that has been our area, and we will be love to understand more new basins. Our toolbox, as we built over time, is the very successful partnership with Open Detect. We represent them in Canada, and we use all of their plugins and those, and test it and do studies, as well as we apply in our services and or combine services with them. Then QStrat is we are building the just log analysis and various cross section, and it's called QStrat well log based analysis of the sequence stratigraphy, the new workflows and deep learning development of correlating, auto-correlating tops and those. So that is the area we will cover in a couple of weeks. And then inversion with Hampson Russell is our key for AVO and inversion work. And software we use for petrophysics is GS software out of Florida. So just wanted to introduce one more thing, that OpenDetect Pro Geoscience package is one which is actually quite discounted for all the plugins. So if you really want to go through the workflow, it is really beneficial to be as a complete system, which contains Horizon Cube and all the DGB plugins bundled together into a neural network, deep learning, and dip steering, fault and fracture. Everything is included in the in one package, and it can be as low as like daily, like a 1 or 2 days or 5 days. You can license to get things done, like some of the big workflow. So let's go directly to fault and fracture tools. So the most prominent tool which I've used over time was the similarity or coherency or asimilarity or whatever you can call it. And it's the edge detection tool, like being volumetric or surface based, was introduced a long time with Bahorich and that back in 1995. And that's since been the core of all this, but then it has been so many different ways it has been adopted to carry on with the future. So that is in the base system, the similarity. Then the next big toolbox which comes is the dip and azimuth analysis. So dip and azimuth, or which called structural steering at some point, and it's also called the dip steering plugin in the OpenDetect domain. So it defines the volumetric dip of the, so inline and crossline dip, or a combination of inline crossline dip and azimuth. So each of the small segments would have a dip and azimuth at every local reflector point. So every reflector, based on the entropy of the reflector, you would have a dip and azimuth calculated. So this has been the base of many of the curvature analysis in the. So dip and azimuth is, but by itself, dip and azimuth have a lot of information in it. So over the surfaces, if you can drape it over surfaces, or look at the these are almost change in dip will be clearly managed as breakup of the reflectors. So that leads to volume curvature. So volume curvature was introduced again almost same time, but then it have the basically it is the radius of the circle, so inscribed circle from any curve. So you have most positive curvature when circle is the tightest enough, and most negative when it is the so there is various definitions of the curvature, which is actually defined very nicely in this diagram. So if you take, and it can be then put in a volumetric sense in a 3D plane with various factors. So most often used is most positive curvature, but we also use what called contour curvature, or if you look at your hand. And but the most important idea of this curvature analysis is that at every step out, the curvature effect changes. So sometime if your step out is very big, you won't see the fault, because your not steps out are different. At different step out, the structure will implement differently. So if you look at the structure like most positive curvature, you can almost see very defined faults. But if you look at it very close, they would be displaced on the upper side of the fault rather than the lower side. And most negative curvature will be on the lower side of the fault, or the on the footwall, on the hanging wall side, versus footwall side would be the most positive curvature. And if you look at the gradient of curvature, you would see the fault by itself as the plane cuts through, most negative and positive, that would be the gradient as the change. But faults are contained in the highest gradient where the curvature changes. It's not that usually anticline don't show up as a curvature because they are wider. So what we did, and it was work we presented in 2017 to 16 in Australia, was in AAPG, that you can actually differentiate norm faults from the acquisition artifacts by using different apertures. So if you do use different apertures, you can actually take various step outs and then combine them through neural network. So that's what we did to combine. If you combine them through neural network, then you could differentiate the original. So it will change the amplitude of the original curvature from the acquisition artifact. So that is a very good, strong application of narrowing down into what are the acquisition, because acquisition artifacts would behave very consistently over different curvatures, while the faults itself only would tune in into one or two or three different step outs. So various faults could be then separated from the acquisition artifacts, or at least minimize the effect. But that was before the introduction of this Dave Hill's algorithms and all these. So that is where our new work went into. A lot of unconventional, and those is based on this work. So Dave Dave Hale and Xin-Ming Wu and the whole team of the Colorado School of Mines put in together a lot of algorithms and definition of finding a way to extract the fault likelihood. Or so fault likelihood is a probability of faults, and that probability of faults is defined as the in all direction, like 360 degree, it will do, it's kind of scanning of all the data based on the coherency along different dip and as much directions, but with knowledge of how faults should behave. Like, so there is a better knowledge applied in here. And then they presented a lot of work, and what you can see, the fault likelihood plus how much is the throw around the fault. So you can actually even tell about the throw of the fault as it decreases and increases. So usually that is the when fault kinematics do require us to see that if the fault throw is maximum in the middle of the fault as it decreases or dies off, or it interacts with the other faults or cross. So they were able to extract the cross faults. So they showed a lot of work on the data set. You can see the fault likelihood, but it is a swarm of the area, or likelihood is much wider than the single thinning of the fault. So they did a fault likelihood, and then from fault likelihood, they created a thinning process. So thinning process allows to reduce the number of samples of the fault likelihood to 1. Like, tries to be as close, or thinning will not make it 1, but it would be really sharpen up the whole system. And then you can see the cross faulting, the even faults which cross each other were separately taken as a plane, which was a big plus to the ant tracking and other tools which were available at that time to be able to extract faults crossing each other into a single planes. So that, because fault likelihood would follow the fault plane without being going into neural network, which ant tracker was doing, is going neural network and trying to create artificial intelligence, while this one is more staying with the geology of the faults. So the tools which OpenDetect fault and fracture plugin implemented contain a whole set of the fault likelihood, thin fault likelihood, and then creating a thin fault likelihood. In addition, they came up with the basement fractures, and now most recently a new plugin implemented is FracTex. I won't cover the FracTex this time, but down the road I would probably cover FracTex once I know more and work with it. So that is a new textural base for fracture analysis. But a lot of tools now available, and I will go over these tools briefly, one by one. So what we see from the previous good solutions of the extracting or finding the faults was able to visualize them and have a good best solutions to visualize even with the tracker, but they were not able to have all the attributes of the faults embedded in it. So that is what fault likelihood brings in. So it brings in the dip of the faults, the azimuth of the faults, the likelihood of them, like probability, how probable they are being faults, and so they can be filtered out by larger faults and the smaller faults with less throw, with no throw, or some kind of noise effects, because there will be linear noise effects could happen, migration artifacts and those things. So in order to distinguish them, that is all the tools. So the fault planes can be extracted, then corrected, and then put in place. So now what we see as a thin fault likelihood is a very sharp. These black lines are where likelihood is very high. So we made it blank. So then you can see this is a 0.3 cutoff. So even you can see the set of faults coming here, which are very low, but would be very precise. So in addition, what they put in is the fault fracture density and fracture proximity. So fracture density is you can take an area, you can define a fracture threshold and put a radius and see where the swarms of the fractures are going. So it is like a single fault will become less prominent than the other swarms of fractures where you have a lot more fractures, but they are in a different direction. You can see this along these two trends. There are a set of fractures which could be of leaking, problems of leaking the play, or have other significance in the unconventional side as well. Or the other is called fracture proximity. And this is very important because the natural fractures usually in the unconventional, natural fractures might be stealing your frac material, and you don't want natural too close to the natural fractures. That's why the seismic scale fractures then can be find out that if you're not in a proximity of natural fractures, but you are in a range where you can frac and then create new fractures so it would not be leaked, or water would not be coming in through the major fracture zones. Then you can change the fracture threshold and proximity, and you can find out about the which fracture area. So that is equal application of these tools to the conventional and unconventional methods. So the other now, after you create the fault likelihood, you can extract the fault planes. And so, which is very important for a structural geologist to find out which families are probably real and which families are not real, which azimuths are the real azimuths versus inline or cross line. What you see in an inline cross line may not be the azimuth direction or the dip direction. Or in this case, we are looking at the strike direction. So the one thing to think about, it's converted now, you can apply a skin. So it's called skin is on any fault plane, you're converting it into a skin. It's still not a plane extracted as a horizon, but it's a skin applied to the fault. Now you can then start filtering it. In order to get them, you can merge multiple faults together. So that's a workflow inside to work together, or filter them out. Like in this case, I just uh, selected certain skin size, which is between this 10,000. So it's a 1,000 is the minimum voxels. The total, it's just divided by total uh, plane area. So the total voxels inside a single skin is defined. Like if you are 15,000 to 20,000, I mean larger faults. I'm just filtering out, so you can filter out these faults, or you can filter it out based on like the depending on the smaller faults. So you can go from larger to larger and see where the larger faults are, what their azimuths are, and making sure that they are not the any acquisition artifact or any merging problem between the 3Ds, and those are not the areas. Uh, so going by the azimuth, and also, or you can filter it out based on the dip. Like so average dip, sometime you want a steeper dip faults to be separate from the shallower dips, so which mean these are the low amount of dip. So from center outward is the dip, and then it is the azimuth. So 0 versus, so these are around at uh, 20, yeah, so it's about 45 degree or less than 45 degree dip is the not that steep faults. So when if I choose this way, that would be steeper faults. The other is you can have yes on the basis of the dips, like only if you want to take out the steeper faults, or based on the azimuth. So it can be divided based on the, this is the like azimuth, a certain azimuth can be can will pick up these faults with these azimuths. Now of course their dip direction could be opposite to each other with the same azimuth. That is another to separate out from dipping to the south versus dipping to the north. So that is the area. So you can select and then have families saved as a separate pieces, and then work with them to narrow down these problem areas. So it's working with the conventional. The many other things you can extract. There is a rows diagram where you can extract a lot of information about the how many faults with the density of the faults, as well as the dip and strike of the faults, like how many have higher dip and strike, or you can separate out and put a fault likelihood uh, attribute on it. So which means you're saying that the fault strength is this better, and the at the bottom it's probably the erroneous increase in to the edges. I want decrease in the fault likelihood as well as fault throw. But right now fault throw is not there, but fault throw will. We do have a capability to calculate fault throw and bring it into the same fault segment. So in this way, you can extract faults and then can show attributes on the faults. You can use those faults without a large number of faults by moving them laterally to extract inversion attributes. Like if you have a shale on one side and the sand on the other side, you can do a Allen diagram. There are various ways to using those faults into a without being not too correct, but at least you will give a idea, at least in the areas of the uh, very high likelihood of the faults. And the what we started doing actually many times, the multi-attribute analysis is there in OpenDetect, but not many interpretation software allows multi-attribute. So what we did is that we blank out the fault likelihood. So we take the fault likelihood and then I give clients the blanked out volume. So which mean they can interpret still in their normal workstation, which doesn't allow multiple blanking. So in that way, you can actually then see that where the faults are, and it can also be used to smoothing while honoring the faults. So we can have a different cutoff. In this case, it's like zero 0.2 or zero 0.3 cutoff. You can have a 0.5 cutoff, so only bigger faults are blanked out. So then you can continue with interpretation, and it will automatically stop. Your auto picking will stop at the faults, which you want to see if the auto picking not spill over the faults. So there is like something we modify, we improvise based on what we have with the clients. The other important output which came from here is the volumetric flattening. Like volumetric flattening is that this is where the throw is calculated on each of the fault, and then you can apply called volumetric flattening. This is the first stage of getting to the RGT volume, or relative geological time volume, which is then flattening it on each of them, and then opening up for the unconformity and have unconformity trackers and those things. So I would say the Dave Hale's original algorithms all the way going down to the full RGT restoration volume is partly implemented in the fault and fracture part, and then horizon picking and then combining. I've seen PaleoScan working on various aspects to go farther, but in reality, then you have to go farther with the RGT volume, and that's where interpreter really comes in. There are various algorithms we apply in order to flatten this. So this is not included in fault and fracture plugin, but we apply internally to provide the flattened volume or restored volume. So this was the fault and fracture kind of attributes on the post-stack side. But in addition, you can have multiple other things, like you can bring in azimuthal AVO or velocity variation with azimuth, or shear wave splitting, which becomes, it depends on how expensive and how much processing you need to get done to make sure that COV processing is done, and then have enough data distribution to do the azimuthal AVO. And but there are really, then specifically we work on the azimuthal AVO projects in order to find the fast and slow shear. In addition to velocity variation with azimuth, so this is the V fast, V slow usually gives you this direction, but azimuthal AVO will give you the planes where fluid filled, especially gas filled faults will slow down the or create the AVO versus along the faults which are not fluid filled or which are wet, you would have a low AVO. So there is a difference in the gradients based on which direction you are investigating. So with azimuth, it would change the amplitudes, and that is the AVO basis. So velocity variation have the same basis. The only thing with the AVAZ, you won't find specifically the direction, but you will find the fluid filled path. OpenDetect can also get the COV distributed and extracted the gradients over the sectors. It won't divide into sector, but you can load it in a different azimuth sector and then work through the cross plotting within OpenDetect. Although we use Hampson-Russell and OpenDetect in combination sometime to come up with the COV gathers. And not with COV gathers, of course, they are done in processing, but taking the COV gathers and then applying the azimuthal AVO path. So in cross plotting, you can find the maximum differences using the volume maths and various between the gradients at different azimuths, and then apply the. There is a very nice paper by Marco Perez in Canadian CSEG recorder, and they completely explains a lot of work which can be done that way, or there are commercial software as well, which we have used in the past. The Hampson Russell have one, and Jason have based on anisotropy for AVAZ. So AVAZ analysis is another. So these are kind of the tools and the analysis. So I will just briefly now go over a couple of studies in conventional and unconventional, and which we have done. But it depends on client to client. Many studies we couldn't show because we work closely with the client. So this is one from the Eocene carbonates in Pakistan. They one of the field, the Concord field, have the two major structures. These being the older structure. This has been newly found structures. There are two structures being drilled, but they have a various faulting terminating at the base of these structures to going down to the deeper faulting as it finishes. So what we did in this case, as I explained before, is that we run the most positive curvature at various step outs. So 7 by 7 is a smaller step out. Then, so you can see a lot finer faults, but you also see the acquisition artifact, or really, this is a shallow clay, so it have a very much interaction of the not processing artifacts of the acquisition footprints, or just binning footprints. And so as you go 11 by 11, you get a little bit better, more precise faulting coming in. At the 15 by 15, you can see the acquisition had been, although direction is the same, but acquisition have been dimmed out while they stand out at 15 by 15 as a fault. And the then at the higher, you have the major fault system at 19 by 19. So then after these taking step outs, we combine them together into a really defining the major structural lineaments using the using the neural network to combine. So you can use also at various attributes, you can use RGB blending, or you can use the neural networks to define the common area. So you have a complete fault system separating out, although the fault is terminating below this, so you won't see the fault normally, but you would see it by the curvature analysis. The other was, I want to bring up the same application of the fault likelihood in Utica shale. There was a paper presented by Hasham and Steve and Hardeep. That was from DGB, and that defines how closely we can see the swarms of the within Utica shale, how we can see the details. So with the major faults being separated out, but again within the shale, and we have seen more and more, it's like a polygonal fault system, plus there are swarms of the high intensity fault systems versus the low intensity areas of the, so there is a, those below 0.3 likelihood, they are like kind of fractures, but they are not the acquisition artifact, but they are bin to bin, could have a fact, but they definitely show up as a especially in the shale, when water is leaving the shale during diagenetic, there is a shale variation. And we did a study in Montney, which I would show after, but so Utica, when really look at in a 3D, it's not that informative on a 2D plane, but right from the, once you start filtering it out, you would start making sense where faults are really oriented to. But again, if you show anyone, like as a geophysicist, like say, oh yeah, well, these are all faults, but that's giving a wrong message, like, because they are all uh, the variation of the noise, and as well as various things, although they have a planar effect, because you can see there is a planar continuity in there. But then you have to use a lot of judgment and your tools. Are they just the amplitude variation coming in? You overlay with various other tools to bring up. So we did the work with all the volume curvature and various things with fault likelihood in Western Canada. What we found is another attribute which works really well. It is not really a curvature from the sense of the plane, but it is called the contour curvature. It have a definition of those all curvature, like the curvature definition, but it is really looking at the highest part of the anticline and the lowest part of the syncline. So it has like lowest part of the syncline in this case is red versus highest anticline is blue. So the contour curvature really gives you the turning of the contour. Like it can be learned this way, the turning of the contour. So when we did actually the study, we end up like to client, we sent a lot of curvature volumes to see test against where their frac is going. So this is extracted over one of the mountain horizon, and I cannot reveal where it was, but there were horizontal wells drilled along. What we found that these high uh, contour curvature patterns do overlay really well where the wells were in. When they were drilling the new wells, they had tracers on the older well, and so they would start getting the uh, frac fluids showing up, or pressure change within the existing tracers. So showing that there is a communication between the well to well on certain these ones. And we were like quite surprised because it was new kind of finding. And since then they have used many times the same uh, like contour curvature, because what it is, it's really within a shale, it's the shale buckling. So within a shale during diagenesis or during the later stage of compression, it is being buckled along the small folding within the shale effect. And that folding is caused by, because shale is ductile at some point, and it created that kind of a small anticline synclines, but it is really within 50 milliseconds. So this is extracted much thinner. So at different step out, we were like step out 4, step out 5. So then you see the larger areas of the change in depth. You can call it a change in the depth and along the strike, but change in the depth. And so that was really quite interesting to see if these are not the regular volume curvature attributes, but it's the contour curvature attribute, which was the really making more sense, especially when you filter out the at a larger step out. So we did like again, you can see the fault likelihood would give various faults, and again you can see the end of the 3D have the artifacts, but the we tried to match with this. But again, for looking at it in more detail into the local structure and effect, that starts making sense. Like if you look at this, now we combined it the same fault likelihood with spectral decomposition, which actually highlights the areas of the better TOC, you would say, like, I know I don't want to take the credit that TOC, then everybody will jump on me that it's not the TOC, but the spectral decomposition, the absorption of the amplitudes within a shale zone, the extraction overlaid with the fault likelihood also give us the indicators of the zones of the uh, different different geological effect within a shale basin. So this is like a really 5 miles by 5 miles the across this area, so which have a lot of these. So we work very closely with them because of course this area is very new and people have the confidentiality for that. So what we wanted to conclude and then have ask if you have questions is it's important to fault and fracture characterization is really important to understand the structural setup as well as the stress directions or present day stress directions as well as various fault families. The unconventional reservoir characterization would have seismic resolution. It need to investigate below the seismic resolution, like especially in the amplitudes and those. So you have to go into curvature domain as well as much finer attributes such as textural. Right now it's doing the textural attributes or, uh, you know, is really a small segment domain. And more importantly, to compare them with the larger domain. So it's like a different apertures, different, uh, so various attributes which you could only make one, you would have like a 12 volumes to combine them together. And especially in fluid flow and discrete fault volumes and those, when you bringing in these information into the discrete fracture network or DFIT volume and those ones, you really, it becomes important that model like fluid flow model or reservoir simulation model incorporate these attributes. So yeah, and it would of course mitigate the drilling risk with that if it's leaking versus then we can combine it with the chimney analysis and find out if there are possible leakage through the faults as well as the if there are fracture zones which are affecting our areas or actually adding to the reservoirs. So small scale fractures could be adding to the reservoirs. So that would conclude that and ask for